Hello, Eric here. Today we're going to be talking about specific impulse. What is it? How do we affect it? And why does it have such a strange unit? I'm going to start out with a disclaimer. This talk really is rocket science. There's a lot of complexity in it. You do not have to understand all of the complexity to understand the basic points. The reality is actually a lot more complex than what I'm going to present. So some of this is oversimplified, much of it is simplified. Please consult with a rocketry professional before starting any rocket design project. So I'm going to start by going back to the rocket equation. And if you want details on the rocket equation, I point you to my solar system road trip talk. Where I talk about the rocket equation and delta V and why that sort of thing matters when we're building launchers and spaceships and that sort of thing. Here I'm just going to talk a little bit about one kind of specific detail. And this is the form where I usually see for the rocket equation. So the delta V, which is essentially how much change you can make in the speed of your rocket or your payload, equals the ISP, the specific impulse, times 9.8 times the natural log of mb over mf, where mb is the beginning mass and mf is the final mass. So those basically differ by the amount of propellant you burn between those two times. So it kind of makes sense that propellant would be here. It makes sense that ISP would be here because it's kind of a fuel economy sort of measure. It doesn't make a lot of sense why 9.8 is here. That seems like a very arbitrary thing. And in fact, if you've looked into delta V, you've probably seen this alternate equation. And instead of ISP times 9.8, it has VE, or exhaust velocity. And it turns out that what we really care about is the exhaust velocity of the exhaust coming out of the rocket nozzle. So the question is, why do we have ISP? And this is kind of interesting, and I can come up with two good reasons why specific impulse is used so much. And the first one is just number size. If you're looking at exhaust velocity, you look at numbers like 4410 and 3724. And just inherently, as humans, it's easier for us to deal with a number like 450 and 380. It's easier to remember. It's easier to compare them in our head. The other reason is interesting and kind of historical. So at one time, there was a lot of rocket engine development going on in the US, and there was development going on in Germany and elsewhere. And as you probably know, in the 60s, and certainly in the earlier times, the US was using the imperial system, so feet and pounds, the rest of the world using the metric system. So what that means is if you're measuring exhaust velocity, you're measuring in different units. So in the US, you might have this exhaust velocity, 11,896 feet per second. In Germany, you might have an exhaust velocity of 3626. And to compare the two, you have to do conversions. And that just isn't a lot of fun. It makes it more tedious, and you sometimes make mistakes. So what somebody did, and I don't know how this arose, but somebody noted that there was something else that we measure in units that are kind of close to these. Gravity in US units is 32 feet per second squared, and gravity in metric units is 9.8 meters per second squared. So somebody realized, hey, if you just take this exhaust velocity and divide it by gravity, you get this number. And because the units you get are seconds, and seconds are the same in these two unit systems, they end up being the same number. So this is specific impulse. And the process of dividing it to make it the same is often called normalization. We've normalized between the two things, and now we have this thing where we don't have to do conversions. So 370 seconds in US is the same as 370 seconds elsewhere in the world. Now, it turns out, as far as I can tell, in current development, everyone's using the metric system, at least the engines I've looked at in the US, and we still use specific impulse, not really because we need to normalize, but because it's what we've traditionally used and the smaller numbers are nicer. You will find, if you dig into different things, you'll find a definition for specific impulse, which says something like the number of seconds 1 pound of fuel can produce 1 pound of thrust. And that is a true definition. Unfortunately, it's not really a very useful definition. It doesn't have an engineering use. And the real reason we do it in seconds is that's what ended up when we did normalization. So, and that is why people talk about specific impulse, and they never actually talk about seconds when they're talking about it. It really just doesn't matter. So I want to move and talk about exhaust velocity. And in this talk, I'm going to flip between exhaust velocity and specific impulse. Sometimes I'll talk about one, sometimes I'll talk about another. As I just showed, they really just differ by this constant. So anything that makes exhaust velocity higher makes specific impulse higher, and vice versa. So we just some of the concepts are easier in terms of exhaust velocity. Some of them are easier in terms of ISP. So if we want to calculate exhaust velocity, you can dig into the engineering textbooks and you come up with a nice equation like this. And of course, you want to know what all those terms are. So these are the terms on the side. Luckily, for sake of this talk, I don't actually want to calculate exhaust velocity. What I want to do is figure out what the various factors are that likely influence exhaust velocity in rocket design, in engine design, and then figure out what changes or what approaches or what trade-offs designers are making trying to get a high exhaust velocity. So I'm going to pull a few things out of this equation. The first, TC, combustion chamber temperature, so how hot it is inside your rocket engine. We want that to be higher. So if that goes up, exhaust velocity goes up. Second term, I'm going to call this nozzle pressure factor. This one's a little complex. We'll go into more details. We also want this to be higher. If that's higher, exhaust velocity goes up. And then finally, we have R gas. And the little note on the side says exhaust flow specific gas constant, RR divided by MM. And RR is universal gas constant, and MM is really something very interesting, exhaust gas molecular weight. Now we want R gas to be higher. This constant is just that, a constant. So that means we want exhaust gas molecular weight to be lower. Two caveats. The first thing is beware the square root here. So because of the square root, even if we doubled everything inside the square root, we'd have to apply the square root. So if we could double this gas constant or double the combustion chamber temperature, we only get 1.4 times in the exhaust velocity and the ISP. So double this and you get 40% more ISP. There's also a mystery factor that also plays in here that I'm going to talk about later. It doesn't really show up in this equation. So start with the first one, combustion chamber temperature. Higher temperatures give higher ISP. Unfortunately, higher temperatures can also make things melty. So here we have a little picture. I had a hard time finding failure pictures or failure videos of rocket engines, kind of surprisingly. But this is a little test engine, and you can see there's a lot of thrust coming out of the bottom, and near the top of the engine there is stuff coming out to the side. And that's because the combustion chamber got too hot and it got melty. The temperatures that you can run are really limited by the materials you're using and how much cooling you have. What that means is that from that perspective, you can't really change a lot of things. You kind of get, based on your material, on your cooling, you can run at a specific temperature and you're just kind of stuck with that. Nozzle pressure factor is a little more interesting. So here's the full term, and the big things I care about here are PC, which is the pressure in the combustion chamber. So how much pressure we have there, and then PE is the nozzle exit pressure. Now, the equation is a little weird since it's 1 minus. What we want is we want PE over PC to be as small as possible. And therefore, we want high combustion chamber pressure. That makes the denominator big, which makes the overall factor small. And we want low nozzle exit pressure. That makes the numerator small, and therefore the overall constant small. So go through them one at a time. Combustion chamber pressure. So the ISP that you get out is actually fairly closely correlated to your combustion chamber pressure. We see a little graph here. This is for an ethanol rocket. Across the bottom, we have what's called mixture ratio, the ratio between the oxygen, the oxidizer, and the fuel. Talk about that more a little later. And what we can see is starting at the bottom curve, 700 psi, and we just keep increasing chamber pressure and things keep going up. So this looks great. You know, we keep increasing chamber pressure, we keep getting more ISP, so that looks pretty straightforward. The problem is that increasing chamber pressure is difficult. So this is the RS-25 Space Shuttle main engine. I chose this because it particularly exhibits the problems you run into trying to run high chamber pressure. So the yellow box denotes the fuel turbo pump. So this is the pump that is responsible for pumping the fuel, in this case the liquid hydrogen, into the engine. And to create a high pressure, you need to pump a lot of propellant very quickly. This pump runs at 32,000 RPM. It generates 73,000 horsepower. That is not a typo. Just pumping the fuel requires 73,000 horsepower. That does not make it an easy thing to design. So turbo pumps are very, very difficult to design. And especially in this case, the hydrogen one is hard because hydrogen you have to pump a lot because it's not very dense. The oxygen one on the other side of the engine, if I recall right, runs at 25,000 RPM and only requires about 23,000 horsepower. So it's a little easier to design. So combustion chamber is great. You need to have advanced turbo pumps to be able to do it, and that is hard. Now let's go look at nozzles. And nozzles are really kind of interesting. And I'm going to talk about the bell nozzle, which is pretty much what's used in every rocket engine right now. And what we are trying to do is choose the right nozzle size based upon the altitude where our rocket is operating. So if your exit pressure, so let me explain this. Starting at the top, we have the combustion chamber. So remember, we have very high pressure there. As the exhaust gas comes through that, the nozzle gets bigger and bigger, and that expands out the exhaust. And when it expands, it gets to a lower pressure. And what we want, in the upper right here, it says exit pressure equals ambient pressure. So we want the pressure right at the edge of the nozzle there to be exactly the same as the pressure outside the nozzle. And when we get that, the exhaust plume comes straight down. It's in the shape of a column, and that gives you the most efficiency. And the reason why is it's all going down, and that means all the force you're getting from it is going up and pushing your rocket up. So that is what you want for the best efficiency and the best ISP. So let's assume this nozzle is operating, say, at 5 or 10 kilometers in the air. Take that nozzle down to sea level and something different happens. What happens is the air pressure is equal, not at the exit of the nozzle, but higher up. So what happens is as soon as we reach that point, the air from the side presses in and the exhaust plume is pinched together, and that means we lose efficiency. This is called being overexpanded. The nozzle is trying to expand the exhaust gas to a lower pressure than we actually have. Now it turns out, if you've ever seen something like this in an exhaust test, or you see it behind airplanes sometimes, these are called mock diamonds. And mock diamonds look really cool, and they're kind of considered to be the sign of efficient combustion, but they're actually the sign that your nozzle is overexpanded. It's actually not the optimal nozzle for the current air pressure. Now, not surprisingly, at sea level, we see one thing. If we get to high altitude or we get up into vacuum, this same nozzle, we will see something else. So now we get to the end of the nozzle, and the pressure there is higher than the pressure outside. So what happens is the nozzle doesn't keep the exhaust going down. The exhaust kind of leaks out to the side, and you lose efficiency because of that. This is called underexpanded. The gas, when it hits the edge of the nozzle, has not been expanded down to the ambient pressure. If you watch Falcon 9 launches, you will see this all the time on the first stage. When it starts, when the first stage launches, the exhaust comes straight out the bottom like the middle picture. And once it gets up, gains quite a bit of altitude and it gets close to staging, the exhaust comes way out to the side. That is because the nozzle is underexpanded. So the big point here is that your best exhaust velocity comes from a nozzle that is neither over or underexpanded. But if you are using a standard nozzle, you're always making a compromise, at least if you're operating in different air pressures. So you can't design a nozzle that works great at sea level and then works great at high altitude. It just does not work that way. The physics does not work that way. It may be possible to do that with what's called aerospike nozzles, but nobody has actually really built commercial engines with aerospikes, as they have some other issues. So that is nozzles. You remember we had a term there in that equation for exhaust gas molecular weight. And that's what I want to talk about now. And I'm not going to talk about exhaust gas. I'm going to talk about kind of this physics example first. So here we have two carts. Think of them as railroad carts. On the top one, we have 10 balls. Each of them weighs a kilogram. So think of these kind of like cannonballs. The bottom one, we have 4 balls. Each of them weighs 2.5 kilograms. So total, we have 10 kilograms up top. We have 10 kilograms down below. And you can think of this as our fuel, or our propellant is probably a better term. So starting at the top, we take a ball, we put it into our cannon on the back. We add a little bit of explosive or propellant charge. We ignite it, and the ball comes out the back. And just for sake of argument, let's assume that it comes out at 100 meters per second. And the question here is, how much force forward are we going to get from that? And, well, we can do that by figuring out the momentum, which is just the mass times the velocity. So 100 kilograms times 100 meters per second gives us 100 kilogram meters per second. And if we know the weight of the cart and the balls, we can divide that momentum by the weight, and that will tell you how fast our cart is going forward. Now let's look at the bottom. We're going to do the same thing. Take a ball, put it in the cannon, put the same propellant charge in, and fire it. And we notice it comes out slowly, and that's not a surprise, it's heavier. And how fast it comes out is roughly going to be proportional to the weight. So I'm going to say 40 meters per second. We do our momentum calculation, 2.5 times 40 still gives us 100 kilogram meters per second. So we get the same push forward. And okay, that looks fine. It looks like we have something that's equivalent. But the important thing to look at is our fuel economy here. The top case, we have 10 of these balls. So 10 times 100 kilogram meters per second gives us 1,000 kilogram meters per second. The bottom, we only have 4 of them. So 4 times 100 equals 400 kilogram meters per second. So what did we find out? In terms of fuel economy, throwing light things fast is much more mass efficient than throwing heavy things slower. Okay, now let's apply that to what we're talking about, to exhaust velocity. And I'm going to look at some specific engines here. I'm also going to give you a warning that this has some chemistry in it. If you didn't enjoy chemistry in high school, you might have some flashbacks, so you might want to be prepared. If you don't remember your high school chemistry or you never took chemistry, you don't have to understand the details. So I'm going to start by looking once again at the RS-25, the Space Shuttle main engine. This engine burns liquid hydrogen and liquid oxygen. And if we look at our chemistry, we take an oxygen molecule and 2 hydrogen molecules, and we put them together, we ignite them, and we get 2 water molecules out the other side. And this is what would be called in chemistry a stoichiometric equation. And by that it means we've balanced on the same on the 2 sides. You'll notice there are 2 oxygen molecules on the left, there are 2 on the right. There are 4 hydrogen molecules on the left, and there are 4 on the right. Now, an interesting thing we can do is we can look at the atomic weight of our propellants. So an oxygen weighs 16, so there are 2 of them, so we have 32. Hydrogen weighs 1. There are actually 4 of them here, so we have 4. So in terms of weight, we would get a mixture ratio of 8 parts oxygen to 1 part hydrogen. So you can think of this, if you're building the rocket, 8 kilograms of oxygen to 1 kilogram of hydrogen. Now, it turns out that that is the mixture ratio that gives us the most complete combustion. But if you go and look at an RS-25, you will see that the mixture ratio they list is 6.03 to 1 rather than 8 to 1. And there are actually a couple reasons for this. One reason is that if you run at the ideal mixture ratio, you get hotter combustion. And you remember I talked about things getting melty if they get too hot. So that's one of the reasons. But there's a really interesting other reason that's going on. Oh, actually a second reason. When you're building a rocket engine, inside the combustion chamber, you do not get perfect mixture of these 2 propellants. So some places of the combustion chamber will have a little more oxygen, some will have a little more hydrogen. So what that means is if you ran at the ideal ratio, you would have spots that have a little free oxygen. And you would have free oxygen at very high temperatures. And free oxygen at high temperatures just wants to eat up the inside of your engine. So generally engines do not run at that sort of ratio, even if that would be fine from a temperature perspective. You just want to make sure you don't have any free oxygen there. Now the third reason is actually really kind of an interesting one. So based upon this amount, 6.03 kilograms of oxygen and a kilogram of hydrogen, you can do the chemistry and you can see that that leads you to 6.79 kilograms of water. Now that's less in weight than the 2 things coming in. And we know that the weights have to match. So what is the other thing coming out? Well, we have more fuel than we need. We're running fuel rich. So what comes out is a little extra hydrogen. Why do we care? Well, we can do the atomic weight thing again. Water has an atomic weight of 18, 16 from the oxygen, 2 from the hydrogen. The hydrogen has an atomic weight of 2. And if we look at how much total we have here, we can do an average and come up with an average exhaust weight of 17.5. So that means in our engine, we have quite a few of these big water molecules coming out. They come out fairly slowly because they're heavy. And then we have a small amount of these hydrogen molecules coming out, and they come out pretty quickly. So that was one engine. Obviously, I'm going to look at a different engine. So if we look at the Raptor from SpaceX, it burns liquid methane and liquid oxygen. And we're going to go through the same analysis. So the equation here, 2 oxygen molecules plus a methane molecule gives us carbon dioxide, CO2, and 2 water molecules. The atomic weight, these 2 oxygen molecules, atomic weight is 64, 16 for the methane. We get a ratio of 4:1. And that's the ideal ratio. What would you expect? We'd expect that it's a little lower because we want to run fuel rich. Interestingly, it's not as much lower as we saw on the RS-25. Here, it's maybe just 10% off. And the RS-25, going from 8 to 6 is actually a pretty big jump. We'll kind of figure out why coming up. So I can do this math. What do we get? Get about 2.5 kilograms of CO2, about 2 kilograms of hydrogen, and a tiny little bit of unburned methane coming out. Okay, the atomic weights, CO2 is heavy. So those 2 oxygens are 32, plus the carbon gives us 44. The water we already saw was 18, and the methane we already saw was 16. So this gives us an average exhaust weight of a little under 32. Okay, obviously much higher than the liquid hydrogen one. So we have these big CO2 molecules coming out, kind of smaller water ones, and a little bit smaller, about the same size methane ones coming out. And because of that, our exhaust velocity is going to be lower. Now I need to put a little asterisk here over on the mixture ratio. And the reason I put an asterisk here is because of the Raptor design, SpaceX very likely has the ability to tune or change the mixture ratio. And they may actually do that during flight. So when you take off, generally you would want a lot of thrust, which means you want as much combustion as you can get within the limits of cooling. So 3.6 seems like a pretty reasonable place to be for liftoff. They have a lot of combustion and enough methane coming out that you are going to keep your engine fuel rich enough so you don't damage it. However, once you get up in flight a little bit, you burn off some fuel, it may be that ISP is more important than thrust. And one way you could throttle down your engine is you could just reduce the amount of oxygen you're putting in. What would that mean? Well, that means the equation on the right would shift, and you would get proportionally less CO2 and hydrogen, and proportionally more unburned methane. What would that do? That would drive your exhaust weight down, and that would actually increase your ISP. So now I've looked at the two. You're probably not surprised I'm going to compare them. The average exhaust weight was 17.5 to 31.9. So the ratio between that is 1.8. Remember I said we had to remember the square root. So the square root of that is 1.35. So if all things were equal, all we had was the difference in propellant, we'd expect that the RS-25 would have a exhaust velocity and ISP about 35% higher than the Raptor. So go and pull some numbers. Vacuum ISP, the RS-25, 452.3. The Raptor estimated to be 348, so the factor is 1.3. I first ran these numbers and I was pretty excited. It's like, hey, this looks like, all these calculations make sense. Well, then I ran the sea level numbers. 366 versus 333, 1.1 is the value we get. And that is not 1.3. And there are a couple things going on here. I think the first thing is simply that Raptor is a more advanced engine. It runs at a considerably higher chamber pressure. And as we know, chamber pressure will give you more ISP. So we wouldn't expect to see this exact ratio. But there's something else interesting going on here. And I think it's a really interesting point in engine design. As close as possible, I tried to make these the same scale. And something you may have noticed, the RS-25 has a nozzle that's 2.3 meters across. And the Raptor has a nozzle that's 1.3 meters across. So quite a bit different in nozzle size. So remember what we talked about in nozzles? So what that means is we would expect that the RS-25 has more of a high altitude nozzle and the Raptor has more of a low altitude nozzle. Is that expected? Well, I went to flightclub.io, which is a great resource, and I found some simulations of the shuttle. So this is what we would expect on a shuttle flight. And I also went there and grabbed one for a Falcon 9. I thought about, they had one for Starship Super Heavy, but I think it's a little too speculative, and I can make the same point with the Falcon 9, so I chose to do that one. The same points make sense. If we look at the Falcon 9 chart, we notice in this little square, this is the place where the first stage engines are running. So that Raptor we showed will be the same. It's a sea-level Raptor designed for the booster. So that's where that engine runs. And because it only runs here, it sees this range of air pressures. So at sea level, it's 0. And then up to staging, when it stages, it's pretty much nothing. So what that means is SpaceX has therefore chosen a nozzle size that makes sense for that range of pressures. They need to have efficiency at sea level, and they also need to have efficiency up high. So they've chosen this nice compromise nozzle. They also need to be able to fit 9 of them in the back, and that may have affected it a little. So we'd expect a relatively small nozzle. The design for shuttle is really different. So if we look over here, this box shows the range that the RS-25 needs to run in. And what we see is that the vast majority of the time it spends burning is pretty much in vacuum. Above 50 kilometers, there is not much air there. So that means from an overall efficiency perspective, having a bigger nozzle makes a lot of sense. You can actually make the argument that the shuttle, the RS-25, is really the second stage engine for the shuttle. The first stage engine is the boosters. And it does run starting at the ground, but the vast majority of the thrust comes from the solid rocket boosters. So if you want to optimize that engine, you want to optimize it for the time after the solids burn out. And that's pretty much only in vacuum. So that's one of the reasons the RS-25 has such a high vacuum ISP. It has a very high vacuum ISP because it's not really a sea level engine. It can run at sea level, but it's not efficient there. Where the Raptor and the Merlin that's on the Falcon really is a booster engine, and it needs to be very, at least reasonably efficient at the low altitudes. So let's go on and look at another engine. So I wanted to look at another advanced engine, so I chose the RD180, which is probably an equal technology sort of engine. It runs on RP1 and liquid oxygen. And so I wanted to do the same chemistry analysis, so I started doing some research, went out and found the analysis of what RP1 is. And of course, RP1 is just kerosene. And I found that listed in this table. And you can see there are 15 different components. And then there's this table. And there's also these two tables. And at that point, I just pretty much gave up. You can go and find some estimated equations. And here's one that it looks like. And you really cannot do the kind of analysis I want to on this because C12H26 is a average, and it's a bunch of molecules put together, not individual molecules, and this just was not going to work. So I just basically decided to abandon looking at RP1. I did want to look at two other interesting cases, and these are non-chemical rockets. So these are two cases where we're getting thrust not by burning chemicals, by burning the propellants, but by doing something else. And the first one was a nuclear thermal rocket. And I have another link here if you want to know about nuclear thermal rockets. I have a talk that talks about all the details about them and why they're good and why I think they might not be as good. So go watch that if you want the details. Now, nuclear thermal rockets, I'm going to write an equation. This isn't chemistry because we're not doing chemistry. We take liquid hydrogen, we add a bunch of heat, and we get hot hydrogen. And we can do the atomic weight thing. We start with 2 and we end with 2. And this is why nuclear rockets look so impressive or look so interesting. You remember on the RS-25, we were about 17.5. Here, our exhaust weight is 2. And remember, from an efficiency perspective, smaller is better. So, the engine, we have this nuclear core. We put hydrogen into it, and out of it, we get hydrogen molecules, and they come out really fast. So, let's compare two engines. The RS-25, once again, SNRE stands for Small Nuclear Rocket Engine. I'm going to use the numbers from the SNRE Enhanced, which is kind of a little bigger version of this. I've tried to make them the same size. The SNRE may actually be a little smaller here. I think that it's running a vacuum nozzle. So the nozzle may actually be bigger than the one we'd expect on the RS-25. So remember, average exhaust weight, 17.5 to 2, 8.75, take the square root, 2.96. So we would expect that if we can get the same things going on in the combustion chamber, we would expect that this thermal rocket would have an ISP about 3 times the RS-25. Now, vacuum ISP, RS-25 about 450. SNRE is asserted to be about 900. That's what the designers thought. Most nuclear rockets were never built. So that would be a factor of 1.9, which means we really aren't seeing a factor of 3. And I suspect that the nozzle for SNRE is actually bigger than the RS-25 because most nuclear rockets these days are designed to be used in orbit because if you try to use them from land, you spew radioactivity all over the place. So I wouldn't expect that there's a nozzle difference. If anything, I'd expect the nozzle difference would help the nuclear engine. So the question is, why are we seeing this? Well, decided to go look at exhaust temperature. RS-25 is supposedly about 3,500 degrees Kelvin. SNRE is supposedly about 3,000 degrees Kelvin. That would give us a little factor, about 10%. So that's not really the factor going on. I went and looked at some of the records from the thermal engines, nuclear thermal engines that were actually built. And it looks like they were running much, much cooler, maybe 2250, maybe even down to 2000 degrees Kelvin. And I suspect that my guess of 3000 is a little high. If we did that, the ratio between those, we can expect maybe 25%. So that accounts for part of the difference between what we get here and what we actually get from an RS-25, but it doesn't really account for all of the difference. And I really don't know why we wouldn't see as much. There's clearly another factor going on. And of course, in this comparison, go watch the video. There are other factors that make nuclear thermal rockets really not very exciting. So the final rocket I want to talk about is an ion thruster. And this one is also not chemical. This one is actually electric. And I chose a real engine here that is used on communication satellites. And this is going to look really confusing. So ion thrusters use typically xenon, sometimes they'll use krypton, so inert gases. The xenon molecule is really big. It's 131 in atomic weight. And that seems to go against everything we learned earlier when we were doing the chemical approach. But the ion thrusters really work very differently. So we take that molecule, we put an electric charge on it, and then we use an opposite electric charge on a grid, and the molecule comes flying out. And it comes flying out extremely quickly. And so it turns out in this case, I said that small molecules fast are better than bigger molecules slow. This is a case of bigger molecules very fast. So these give very impressive ISPs, about 3000 for this thruster. And that is, you go buy it off the shelf and it'll give you 3000 in ISP. And that's very impressive. There's a little problem here. The thrust is 200 millinewtons at 5,000 watts. As I said, it's an electric thruster. So if you have 5,000 watts of electric power, you put that into this thruster, you have a supply of xenon, and it will give you 200 millinewtons of thrust. Just for comparison, that RS-25 is 2 meganewtons of thrust, or about 10 million times more than this thruster can give you. So what does that mean? It means you can use ion thrusters to get small amounts of thrust but run them for a very long time. And that works great if you have a supply of electricity. And the reason you use these in communication satellites, the communication satellites already have to have a lot of solar cells to produce the power they need to operate. So you already have a power source there. And what that means is, with that power source and a thruster like this, or maybe multiple thrusters like this, it takes very, very little propellant to move from one position to another. So what that means you can have more satellite, less fuel. It also means that you can run your satellite for a longer lifespan on the amount of fuel it has. So that is why these thrusters have essentially taken over for communication satellites. You don't see chemical rockets on them anymore. However, of course, you don't get much thrust. So it only works in cases where, going from one orbit to another might take months. If that's okay for you, great. These are a great choice. We're finally going to get to the mystery factor. And this is about engine cycles. And cycles in this term are different ways of building your rocket engine. And I'm not going to go into details here. But there are basically two different classes of engine cycles. And basically the problem is, remember I showed you the turbopump earlier, you need something to drive that turbopump. So a very simple design is called combustion tap-off. You put a pipe on the side of your combustion chamber, the gases come out, and you feed that through the turbine. There's another one called a gas generator, where you have this separate combustion chamber called either a gas generator or a pre-burner, and it burns some propellant. You run that through the turbine, and that drives your pumps. So both of these have kind of a downside. The exhaust that comes out of that turbine goes overboard. So it means it's not going through the nozzle, so you aren't getting the benefit of the momentum from that exhaust. So that has the equivalent effect of increasing, you can think of it the same as increasing your molecular weight. You're essentially throwing away some of your propellant. So here's a nice SpaceX Raptor on the side there. We actually have the gas generator. I'm sorry, it's a SpaceX Merlin. We have a gas generator on the side, and as you can see, the gas that comes out of that does not go into the nozzle. There are some other designs you can do. This is a F1 engine from the Saturn V first stage. The gas generator also on the right here. The output of that comes out of the gas generator, and then there's this weird duct that wraps all the way around, and it is injected into the nozzle. You primarily do that for cooling purposes. The F1 does that. The Merlin vacuum also does that. You do that to keep the outer part of the nozzle cool. It's really not a big benefit from ISP as far as I can tell, because you have bypassed the combustion chamber. You get a little expansion between that point and the nozzle exit, but not really a lot. So you'd obviously like to avoid throwing away some of your propellant. So here's another cycle. This is called the expander. And you don't burn fuel to drive the turbine. You just heat up whatever your cold fuel is. So if you have a liquid cryogenic fuel, like liquid hydrogen, or you can do it with the oxidizer, with liquid oxygen, you heat that up in the nozzle, it expands, and it drives your turbine. So that means all of your fuel goes through the combustion chamber. That's good for ISP. There are some problems with expander in that it's hard to get a lot of power out of an expander engine. And then finally we come to stage combustion, which is kind of the holy grail. And in the stage combustion, you have a preburner, or sometimes you have multiple preburners, and the output of that drives your turbine, but then you take the output from the turbine and that goes into your combustion chamber. So this gives you kind of the benefit of both designs. The disadvantage here is it's very hard to build. Your preburner has to run very hot because it has to have more pressure than the combustion chamber. So these are hard to build, but they work great. And all of the three engines I talked about the RS-25, I talked about the Raptor, talked a little bit about the RD-180. All of those are stage combustion engines. So let's do a little comparison between two engines to see how much stage combustion gets you. Here we have the Merlin again. On the right, we have the RD-180 made by Energomash in Russia. You probably noticed it's upside down. That's the way they have it stored. They both burn RP1 and liquid oxygen, so this should be a fair comparison. Sea level ISP, 282 versus 311, factor of 1.1. Vacuum ISP, 311 versus 338, 1.09. So it's pretty close, and what that suggests to me is these have similar nozzles. They're both designed as booster engines, so we'd expect them to have similar nozzles. And that suggests that you get about 10% out of going stage combustion. And 10% in ISP is a lot. The difference between 282 and 311 in terms of payload, in terms of delta V you get, is much more than you would expect. So that's why everyone wants to build stage combustion engines. So a little bit of a summary. The differences inherent in the chemistry of different fuels have a big effect on exhaust velocity and therefore ISP. Liquid hydrogen and liquid oxygen will just give you a higher exhaust velocity. Liquid hydrogen in a nuclear thermal engine will just give you a higher exhaust velocity. Now, there are other trade-offs other than exhaust velocity in ISP. There are other reasons why you might prefer a different fuel. Higher chamber pressure and temperature is great if you have materials that can survive both the chamber pressure and you're good enough to build the turbopumps. The nozzles are really chosen based upon the operational environment and the size constraints you have. You really are not optimizing nozzles kind of in the same way you optimize engines. You just choose one that makes sense for whether you're doing a sea level engine or a vacuum engine or something in between. Some engine cycles steal propellant and result in a lower ISP. Gas generator engines are great. You'll lose ISP, but they're a lot easier to build. Exhaust velocity makes more sense than specific impulse in terms of engineering discussions, but we're kind of stuck using specific impulse because everybody understands it and it's easy to compare. So, thanks for your attention. Please like the video and please subscribe.